From the most general perspectives of thermodynamics, the difference between real and ideal solutions consists in the additional energy of interaction between the particles, ions in this case, in real solutions. Thus, the thermodynamic potential of a real solution is equal to the thermodynamic potential of the ideal solution plus the thermodynamic potential of interaction between the particles, the ions, in the real solution. We can relate these thermodynamic potentials to the number of moles of component I, while the number of moles of the rest of the components are held constant, as well as the pressure and temperature. These are, however, the chemical potentials of the real and the ideal solution, as well as the chemical potential of the interionic interaction. And this is how we symbolically denote these chemical potentials of the component I. As far as thermodynamic potentials go, it is known that the differential of the thermodynamic potential G is equal to the negative product of the entropy and the differential of the absolute temperature, plus the product of volume and the differential of the pressure, minus the differential of the so-called non-volume work. This work does not depend on pressure. We can rewrite this expression, and after the rearrangement we see that obviously the first and the third term on the right side of the equation are zero because temperature doesn't depend on pressure, and as we mentioned, this non-volume work also does not depend on the pressure. And we obtain the following equality. On the other hand, the thermodynamic potential G is a function of the pressure, temperature, the number of moles of component 1, number of moles of component 2, and so on, and the number of moles of component I, and therefore, by definition, the differential of this potential, thermodynamic potential G, is equal to the sum of these terms, where the expressions in the brackets are the partial derivatives of the thermodynamic potential G versus the independent variables which this thermodynamic potential is a function of. And in this case we have the partial derivative of G over T at constant pressure and the total number of moles, N, where N is the sum of all moles existing in the solution. Also, by Nj we denote that the moles, the number of moles of all other components but component I are held constant. We can rearrange this expression too, and we see that the first term and these terms that are included in the sum are zero, because temperature is not a function of pressure, and also the number of moles is not a function of pressure. And we may write, and because, as we saw, this derivative is equal to the volume, we may write, or, and of course we can refer all that to component I of the solution, where Pi is the partial pressure and Vi is the partial molar volume of component I, while μI is the chemical potential of component I. Then from the ideal gas law we have for 1 mole this expression, while for 1 particle we have where Na is the Avogadro number, and therefore, and we can substitute this expression for Vi here. The obtained differential equation can be integrated by parts. And now by rules of integration we have. And finally, and we may call this constant mu0, or where the constant of integration, mu I0, is called standard chemical potential. Now, if we again use the ideal gas law, we see that number of moles over the volume is the concentration Ci, and we can substitute this Pi in the above expression, and then we can rearrange this expression. And because these two terms are both constant, we can merge them into one constant. On the other hand, for a real system, we have, by the same token, notice that for real and ideal system, the standard potentials are the same. And also for a real system, we have substituted activity for concentration. And because activity equals the product of concentration and the coefficient of activity, but these two terms are exactly equal to the above expression. Therefore, and if we compare the last expression with, we see that the partial energy of interaction of the ith ion is equal to kT logarithm of yi, which is also equal to, as we already saw. In other words, if we know the partial energy of interaction, we can determine the value of the activity coefficient yi. To calculate this energy of interaction, we have to know exactly how the ions are situated in the solution and what exact forces are acting between them. Unfortunately, this is not known with precision, and to calculate this mu I, we have to resort to models. Probably it is worth reminding that the derivations we just observed were done as if the particles in an ionic solution were particles of an ideal gas. But then how can one understand the concept of partial pressure in the case of ionic solutions? Without going into much detail into the theory of solutions, we should mention that there is a connection between the partial pressure of a solute and its concentration, or the moles per unit volume of the solute. And such connection is described by laws such as Henry's law, Raoult's law, and so on. Notice also that the interchange we at times used between partial pressure and total pressure is acceptable, because when in a mixture of gases only the moles of one of the participating gases is changing, while the number of moles of the rest of the gases in this mixture is held constant, then this one gas is the sole contributor to the change in pressure in the whole system. Therefore, whether we differentiate versus the partial pressure or the total pressure is immaterial, as long as we're interested only in the form of the relations, as we are here. In such sense should be understood also this symbolic conversion which we did a moment ago. Now we will observe one model of the ionic solution widely used to calculate the energy of interaction between ions in a real solution. This model is the basis of the so-called Debye-Hückel theory. The main idea in this model is that each ion in an electrolytic solution is surrounded primarily by ions of opposite sign, as the disposition of ions in an ionic crystal. Unlike ionic crystal, however, in which the ions have fixed position, in an ionic solution, these counter ions surround the central ion in a statistical sphere, or the so-called ionic atmosphere. This is because in an ionic crystal, the ions exhibit mainly vibrational motion, while in an ionic solution, the motion is primarily translational. The existence of ionic atmosphere, where every ion is both a central ion and also participates in an ionic atmosphere of another ion, is the main characteristics of a real solution that distinguishes it from ideal solution. Thus, the main goal of the theory is to derive an expression for the additional energy that characterizes the total effect of the ionic atmosphere on the central ion in a real solution. The activity coefficients that come out as a result of the theory account for this additional energy through parameters of the solution which are measurable. Debye-Hückel theory is based on several propositions. First of which is that it considers the electrolytes fully dissociated into ions. That's why it's called the theory of complete dissociation. Nevertheless, it is applicable also to electrolytes that are not fully dissociated, with alpha less than unity, if the true concentration of the ions is known. An attempt is made in the theory to account both for the interionic effects, which are of electrical character, as well as for the thermal motion of the ions. Thus, it is claimed in the theory that the distribution of the ions surrounding the central ion is Maxwell-Boltzmann distribution. However, in the first approximation of the theory, the exponent in Maxwell-Boltzmann distribution law is expanded into series, and only two terms in this expansion are retained, ignoring the rest of the terms. In other words, it is considered that the electrical energy of the ions surrounding the central ion is much smaller than the thermal energy of these ions. Here Zi is the number of unit charges per ion, or the valency. E is the unit charge, phi is the potential, K is the Boltzmann constant, and T is the absolute temperature. The lower the concentration, the better this inequality is obeyed. According to another premise of the theory, especially its first approximation, the ions are considered to be just material points, that is, having no volume. And the only property that matters in these considerations is the charge of these ions. This picture is acceptable only for solutions of low concentration. Also, the interactions among ions are considered to be only Coulomb interactions. This also is acceptable only for low concentrations of the solution, because as the concentration increases, the van der Waals forces start to have tangible effect. At that, the thickness of the ionic atmosphere becomes commensurate with the dimensions of the ion, which is unacceptable. Also, at higher concentrations, not only the interactions between the ionic atmosphere with the central ion, but also the interactions of the central ions themselves have to be taken into account. Also, according to the first approximation of this theory, it is considered that the value of the dielectric constant in the ionic solution is the same as the value of this constant in the pure solvent. However, as it is seen from this illustration, for ions existing in solvent water, the value of the effective dielectric constant at near proximity of the ion is much different from the value of that constant in the bulk of the solution. This approximation, again, is acceptable only for solutions of low concentrations, and also for ions of lower valency, because, as it is seen from the figure, for ions of lower valency, the effect of the ion on the value of the dielectric constant is felt at much shorter distances than for ions of higher valency. Debye-Hückel theory, in its first approximation, which is applicable to ionic solutions of low concentrations, is also called Debye-Hückel limiting law. The second approximation of the theory takes into account the finite dimensions of the ions, assigning an effective diameter A to each ion. The magnitude of this effective diameter is determined experimentally because all ions contribute to it. In other words, it is not possible to determine it simply from the crystallographic radii of the ions. In this way, a correcting factor 1 over 1 plus A kappa is introduced, where A is the effective diameter and kappa is a parameter whose meaning will be explained later in the lecture. It should also be noted that in this approximation the effective diameter A is not a constant and may even attain negative values, which is contrary to its physical meaning. Further improvement of the theory led to the retainment of more terms in the serial development of the Maxwell-Boltzmann distribution law. This led to a partial abandonment of the aforementioned condition. Also, this approximation derives the constant value of the effective diameter A. Unfortunately, a value greater than unity for the mean activity coefficient cannot be derived by this approximation. In another development, the formation of ionic pairs between ions of opposite charge is considered, especially for solvents of low dielectric constant. Also, some empirical formulae are constructed containing empirical constants, and upon proper choice of these empirical constants, the values of the mean activity coefficients of more concentrated solutions can be calculated. We'll proceed now by discussing briefly the calculations involved in the Debye-Hückel theory. And these calculations are in fact the solving of one problem in electrostatics for the particular conditions of an ionic solution. Our first goal will be to derive an expression for the potential at a distance r from the central ion, due to this very central ion, and eventually disturbed by the presence of the ionic atmosphere. The electrical potential phi is connected with the charges that cause this potential through the so-called Poisson's equation, where nabla square or del square is the so-called Laplace operator. This is a differential operator of the second order. Phi is the potential, d is the absolute permittivity, where epsilon 0 is the permittivity in vacuum and epsilon is the relative permittivity, the so-called dielectric constant. And ρ is the density of the charges that cause the potential phi. In order to find the potential phi, in other words, in order to solve the Poisson's equation for the potential phi, we have to see what form the expression for the charge density ρ has for the concrete problem we are discussing now. To do this, we will first observe that for the entire solution, or for portions of the solution that are relatively large compared to the dimensions of the ions, we have, according to the neutrality law, this expression, where Ni is the total number of ions of each kind. Or, however, this neutrality law does not apply for an infinitely small volume dV, which is in a constant motion around an inevitably existing central ion. Therefore, according to the Boltzmann's principle, the number of the negative ions having the electrical energy Ez minus phi in excess of the average energy in this elementary volume dV is equal to this expression. Respectively, the expression for the positive ions is the following. Obviously, if there should be an excess of ions of one sort or another, this excess is due to the existence of a potential in this elementary volume. Then the charge of this element will be, and respectively the charge density ρ in this elementary volume dV will be, after dividing by dV. Thus, for all sorts of ions present in the solution, we have for the density of charge in this elementary volume dV. Notice that the potential phi here is due both to the central ion and to the ionic atmosphere. Of course, this potential phi is within the elementary volume dV. In this way, we found the expression for the charge density in the infinitely small volume dV for the particular circumstances we're discussing. And we are ready to substitute it in Poisson's equation. Now this is the Poisson's equation applicable to the concrete conditions of our problem, and we have to solve it for phi. However, in this form, Poisson's equation is still difficult to solve. Therefore, we are going to apply some simplifying assumptions. First of all, we will develop this exponent in series. Then we will suppose that the electrostatic interaction is much smaller than the thermal energy. That is, Ezi phi is much smaller than kT. In such a case, terms of second and higher power will be infinitely small quantities of higher order and can be neglected. Therefore, the exponent becomes, and we can substitute this in the expression for the charge density, and because the first term is equal to 0 due to the electroneutrality law, this is because in this first term we have the sum of all positive and all negative ions in absence of potential. And we can now substitute this new simplified form of the charge density in the Poisson's equation. Or, where kappa is equal to, we should mention that the reciprocal value of this kappa is called thickness of the ionic atmosphere, and we will discuss it further in the lecture. Despite the simplification we made, this still is a difficult equation to solve in its present form. Therefore, we're going to transform the Laplacian operator from Cartesian or rectangular coordinates into spherical coordinates. The transformation is given directly here, and details of it can be found in standard texts of calculus. This transformation is logical since we're looking at a potential at a distance r from the central ion influenced by an ionic atmosphere of spherical symmetry. Also, of the three spherical coordinates, only one of them, namely the distance r, participates in this equation. Now we are ready to solve this equation. In other words, we are ready to find the expression for the potential phi at a distance r from the central ion for the particular conditions we are discussing. Now we'll make a jump here and we'll not discuss the details of solving a partial differential equation of the second order, such as this one, but we'll give its solution directly. As we see, the solution contains two constants, A1 and A2, which we will determine now. From the boundary condition that when the distance from the central ion tends to infinity, the potential has to tend to 0, it follows that the value of the constant A2 has to be 0, because otherwise the potential at infinite distance from the central ion will become infinite, because as we see here, the numerator increases faster than the denominator with the increase of r. Notice also that the first term will be 0 at infinite distance r anyway. Therefore, the second term in this solution has to be dropped. And we have the following expression. In this solution of the equation, which we may also write in the following way, there is still one more constant to be determined, namely A1. The constant A1 is determined by another limiting condition in our model, namely that at infinite dilution the ions are so rare and so remote from each other that practically we can consider there is no ionic atmosphere around the central ion. Therefore, in the expression, the value of the charge of the ionic atmosphere will tend to 0. Now recall that this charge of ions of one sort, appearance of this charge, was due to the existence of a potential, and also in this charge this is only due to the ionic atmosphere, and the central ion is not included therein. So the value of kappa at infinite dilution tends to 0, and therefore the value of this exponent becomes unity. Thus, the solution of the equation at these conditions attains the following form. On the other hand, if there is only a central ion and there is no ionic atmosphere, the potential at the distance r from the central ion will be, where Z central is the valency of the central ion, or these two expressions pertain to the same conditions at infinite dilution. Therefore, we see the value of the constant A1 is equal to this expression. And now we can replace the value of A1 in the general expression for the potential phi. Now we notice that for dilute solutions, for which the value of kappa is low, we can develop this exponent in series and retain only the first two terms in these series. We may substitute this expression here. Which gives, after opening the brackets, or we may also write, we can write this because, as we saw a moment ago, the first term represents the potential at the distance r from the central ion in absence of ionic atmosphere, while the second term is the decrease, the screening of this potential of the central ion when ionic atmosphere is present. And of course the spelling should be corrected here. This is central, and this is also central. In this way, we have now an expression for the potential at a distance r from the central ion, created by the central ion and screened by the ionic atmosphere. Here is also another detail which we can see from this solution, if we substitute the distance r by 1 over kappa, we see that the value of this potential becomes 0. This means that at the distance 1 over kappa, the potential created from the central ion is fully screened, compensated by the ionic atmosphere. Therefore, this value 1 over kappa is called thickness of the ionic atmosphere. Now that we have the formula for the potential phi, we can find the energy of interaction between the ions. This energy will be equal to the energy of charging of the central ion in the electric field of the surrounding ionic atmosphere. Let us have a bunch of charges that create a potential phi at a given point. Then the energy to charge this point from 0 to charge q will be equal to the integral from 0 to q phi dq. And because the potential phi is equal to the charge over the capacity, we may write which is equal to, or, and again, because this q over c is equal to phi, we obtain this energy for charging this point from 0 to charge q due to the existence of a set of charges that create a potential phi. This expression for the energy, rewritten here, is derived from the general principles of electrostatics, unconnected with our model. Fortunately, based on our model, we have already derived expressions for the charge of the central ion and the potential created by the ionic atmosphere, namely this and this. Notice the negative sign here, which makes the product of a positive and a negative quantity positive, because the energy in question is positive. We can write this also as, now we should recall our thermodynamic derivations, and especially this partial energy of interaction between ions. Obviously, this mu Ix is equal to the expression for the energy of interaction which we just derived. Therefore, we may write or and of course we can replace kappa in this expression, or, and then if the number of particles in 1 milliliter are divided by the Avogadro number, then we'll have the number of moles in 1 milliliter, and we can multiply it by 1000 to obtain the number of moles in 1 liter, which is the molarity, Ci. Or, and we can substitute Ni in the above expression. And now, if we want to determine the mean activity coefficient, we can rewrite the above expression to apply for the mean activity coefficient, or rearranging. And now, if we consider that this sum is the ionic strength, we have where B is this whole expression here, which may be written also as, in this way, we derived theoretically, using the first approximation of the Debye-Hückel theory, the already mentioned, experimentally found relationship between the mean activity coefficient and ionic strength. For a 1-1 binary electrolyte, this expression turns into which for room temperature and D equal to 78 becomes Now we will discuss two methods for experimental determination of the activity coefficients. The first method is experimental determination of activity coefficients using the expression for the equilibrium constant. Let us observe the equilibrium presented schematically here, characterized by the equilibrium constant Kc. The quantities participating in this equilibrium constant are the experimentally determined molarities of the species in the solution. If this expression for the equilibrium constant is to be valid for real solutions, as we know, these molarities have to be corrected by the introduction of activity coefficients. Only in such case, this expression, which in fact is derived for ideal solution, can be applied for real solutions too. Also, only in such case, the value of Kc will be constant at any studied concentration. We can simplify this expression a little bit by observing that the value of the activity coefficient of the molecules that are intact in the solution is practically unity, because the van der Waals forces of interaction between the molecules act at much shorter distances compared to the electrostatic forces and can be neglected. Also, as we know, the activity coefficients of the individual ions cannot be determined experimentally, and we introduced the so-called mean activity coefficient. By the introduction of this mean activity coefficient, the non-ideality of the ions of opposite sign is shared equally. Now, we can take the logarithm of both sides of this expression and then rearrange. However, we know that this expression is given by where C is the concentration of the electrolyte and alpha is the degree of the dissociation of this electrolyte. We can substitute this expression on the left side here, and in this way we obtain an equation which we will use for the experimental determination of the mean activity coefficient. First, we observe that the value on the left hand side of the equality can be obtained from experiment. Indeed, since the concentration of the electrolyte is known, the value of the degree of dissociation alpha can be determined through the measurement of conductivity. Thus, we can vary the concentration and each time measure the degree of dissociation alpha and calculate this logarithm. On the other hand, by knowing the concentration, we can also calculate the ionic strength I, respectively square root of I of the solution, corresponding to each one of the studied concentrations. As we know, the value of I, of the ionic strength, is defined by this formula. In this way, we are ready to plot the experimentally found values of logarithm of this expression as a function of square root of the ionic strength. Once we have this graph, the first thing we do is find the slope and the intercept of the initial part of this experimental curve. We immediately see that the intercept has to be equal to the logarithm of the true thermodynamic equilibrium constant Kc, valid for ideal solutions. Because the coordinate is in fact equal to a logarithm of Kc minus 2 times logarithm of the activity coefficient. However, at ionic strength close to 0, tending towards 0, that is at concentration of the electrolyte 0, the value of the mean activity coefficient is unity, therefore logarithm of unity is 0, and the second term is 0. In other words, if we consider the point of intersection of this experimental curve with the ordinate as the beginning of the coordinate system, then this experimental curve is in fact the plot of minus 2 logarithm of the mean activity coefficient as a function of square root of the ionic strength. Once we know the value of the logarithm of Kc, we can subtract it from the value at each concentration, say at this concentration, of the experimentally found logarithm of this expression, rather logarithm of the expression in which the values of the experimentally found conductivities participate. In this way we find the value of minus 2 logarithm of the mean activity coefficient, and it's easy to determine the value of the mean activity coefficient itself. If we now want to analyze to what extent the Debye-Hückel law conforms with the experimental results, we write the expression for the mean activity coefficient derived by the Debye-Hückel limiting law in this way. We observe that the value of the slope of the obtained line from Debye-Hückel limiting law, namely 2b, has to be equal to the value of the slope of the initial part of the experimental curve we just discussed. The second method we're going to observe for the obtainment of mean activity coefficient of ions is based on the determination of solubility product. Let us have a salt of low solubility in equilibrium with the ions it produces in solution. Of course, the concentration of these ions is very low. We may write the expression for the equilibrium constant as if this solution were ideal. The equilibrium constant in this case is called solubility product. If this expression for the solubility product is to be used for real solutions, it has to be corrected as usual by applying the mean activity coefficient. We can now take the logarithm of both sides of this equality, rearrange it, and because the solubility of this salt is provided no common ion is present, we may write now we can start introducing a neutral electrolyte in the solution. That is, an electrolyte that does not have common ions with the ions produced by our salt, and also does not form precipitate with these ions. The only reason for the introduction of this neutral electrolyte is to change the ionic strength of the solution without inducing chemical changes in it. Then, by some analytical method, we can determine the actual concentration of the ions produced by the salt and calculate the experimental value of the solubility product. We carry out the determination of these concentrations after each addition of the neutral electrolyte and then calculate the experimental value of the solubility S to be substituted here. Then we plot the calculated values of logarithm S as a function of square root of the ionic strength. And now, if we extrapolate the initial linear part of the curve to ionic strength 0, then the mean activity coefficient, y plus minus, becomes unity, and the logarithm of it becomes 0. In this way, the ordinate at ionic strength 0 becomes 1/2 of Ks, where Ks is the true thermodynamic solubility product. Now that we have found the value of 1/2 Ks, we can subtract it from the experimentally found value of logarithm of S to obtain minus logarithm of the mean activity coefficient, respectively the desired value of the mean activity coefficient, y plus minus. Now, if the Debye-Hückel limiting law correctly describes the relationship between the mean activity coefficient and the ionic strength, then the slope of the initial linear part of the experimental curve has to be equal to the slope of the theoretical line obtained from the Debye-Hückel limiting law. The form of the theoretical line in this case is in other words, the value of constant B in this theoretical line has to be equal to the tangent of the angle between the experimental line and the abscissa. Before ending this discussion, let us mention one more thing regarding the effect of the ionic strength on the solubility of an insoluble salt. As we know, the connection between the mean activity coefficient and the ionic strength, given in this way, is only true for very low values of the ionic strength. However, in reality, the value of the mean activity coefficient passes through a minimum as the ionic strength increases, and then with the further increase of the ionic strength, the value of the mean activity coefficient starts to increase again, and even may reach values that are greater than 1. Therefore, in order for the value of the solubility product of the salt, corrected for non-ideality, to maintain its constancy, the concentrations of the ions produced by the salt have to increase in regions of ionic strength where the mean activity coefficient decreases, and vice versa. The concentrations of these ions have to decrease in regions of ionic strength where the mean activity coefficient increases. However, each one of these concentrations represents the solubility of the salt. Therefore, in regions of ionic strength where the mean activity coefficient decreases, the solubility of the salt increases, and vice versa. In regions of ionic strength where the mean activity coefficient increases, the solubility of the salt decreases. Regarding the experimental curve which was just discussed, which understandably is quite schematic, we should probably nevertheless mention that in reality the second part of the curve is not ascending so steeply, and also the overall shape of the curve is more symmetric than it was presented. This brings us to the end of this lecture, in which we discussed some basic ideas about the behavior of ionic solutions at equilibrium. Much progress has been made in understanding this behavior, and we could only scratch the surface of it. Of course, a lot more is waiting to be discovered in this challenging and important area of physical chemistry, and it is hoped that this lecture brought some inspiration to the student to pursue further deepening of knowledge in this field.